So today we're going to talk about a different test for showing series are either convergent or divergent, and it is by investigating partial sums. So far we have tests for if a series is an infinite geometric series. We can tell if it's convergent or divergent based on its common ratio. If it's arithmetic, it's always going to be divergent. And then we have the divergence test. So today we're going to add on a different test with the partial sums. So let's look at that. So for partial sums, if the limit of the partial sums exists, then the series converges. So what we're going to look at is if we add more and more things, is there a limit or is there not? If there is a limit, then that tells us that the series converges. If there is not a limit, then the series is going to diverge. So to illustrate this, we're going to write the first 4 partial sums, then find a formula for the nth partial sum, and then use that to determine if there is a limit and therefore if the series is convergent or not. So first we're going to look at the series 2/3 plus 2/9 plus 2/27 plus 2/81. So we're going to find the first partial sum, which means we're going to add the first one term, which is going to be 2/3. For the sum of the first 2 terms, that's going to be 2/3 plus 2/9. Well, 2/3 is getting a common denominator, going to be 6/9. So 6/9 plus 2/9 is going to be 8/9. The first 3 is going to be 2/3 plus 2/9 plus the next one. So that's going to be 8/9 plus the next term 2/27. So getting a common denominator, this is going to be, so we'll multiply by 3 again, so we're going to have 24/27 plus 2 will give me 26/27. Okay, so we might start seeing a pattern there. So 4 is going to be that one plus one more term. So 26/27 plus the 2/81, which when we get a common denominator and add is going to be 80/81. Well, so the first sum was 2/3, then 8/9, then 26/27, then 80/81. So there's definitely a pattern here in those partial sums. So what we want to do is come up with a formula for the nth partial sum. Well, if we look at the relationship between this and this, so looking at the denominator, 3, 9, 27, 81, that's always going to be 3 to whatever that nth power is, and then the numerator is always just going to be 1 less than that. So it's going to be 3 to the n minus 1. Well, what we're looking for here is, are the partial sums reaching a limit? And it should be fairly obvious that, yeah, they are. These numbers are getting bigger, but they're never going to be bigger than 1. This number here is always going to be 1 less than the denominator. So it's going to get incredibly close to 1 without ever reaching that. So what we're going to look at is the limit as n goes to infinity of Sn, which in this case is going to be the limit as n goes to infinity of 3 to the n minus 1 over 3 to the n. Well, 3 to the n, this minus 1 has very, very, very little to do with when this goes to infinity. So we can see this in the numbers, we can see it in the formula. This limit is 1. And if the limit of the partial sums exists, then the series is going to be convergent. So this one's going to go to 1. But the important thing is that it exists and is now a convergent series. So let's look at the series 2 minus 2 plus 2 minus 2. Well, if we do the partial sum, so we're going to do 4 of these as well. 3, 4. So if I add the first term, I'm going to get 2. If I add the first two terms, so 2 minus 2, I'm going to get 0. If I have 2 minus 2 plus 2, we're going to have 2. And then 2 minus 2 plus 2 minus 2 gives me back to 0. So as far as a formula, I'm just going to look at two cases. Either n is odd or n is even. When n is odd, my sum is 2. When my n is even, my sum is 1. So the limit, as n goes to infinity, of Sn, it's not getting extremely big or anything like that, but in order for a limit to exist, it has to go to a single value, and this is going to 2 of them. It is bouncing back and forth between 2, 0, 2, 0. So this limit does not exist. And if the limit does not exist, then the series is going to be divergent. So my next example, investigate the limit as n goes to infinity of Sn for each series if convergent, give the sum. So my first one is Sn is equal to 2n over 3n minus 4. Now this is different than an. This is saying if I wanted to find the sum of the first 100 terms, I would plug in 100. So we're looking at the limit as n goes to infinity of Sn, which for this series is the limit of this. So 2n over 3n minus 4. Well, that limit, since the degree is the same on the bottom and the top, is going to be 2/3. If the limit of the partial sums exists, then the series is convergent. And then whatever the limit is the sum. So the sum of the series is going to be 2/3. Because what this is saying is if I add the first 1,000,000 terms, I'm going to get 2/3. If I add the first 2,000,000 terms, I'm going to get 2/3. So even as n increases, the sum does not change. It has a limit of 2/3. So this is convergent with a sum of 2/3. Next case, Sn equals 3n over 4n minus 5, 4n squared minus 5. So if I look at the limit as n goes to infinity of that, that limit is going to be 0. The degree is bigger on the bottom than the top. Now for the series to be convergent, it has to exist. 0 exists. So this is going to be convergent with a sum of 0. Finally, we have the sum is 5n squared minus 2 over 3n minus 4. So if I investigate that limit, that limit, since the degree is bigger on the top than the bottom, is going to be does not exist or infinity. So if the limit exists, the series is convergent. If it does not exist, the series is divergent. Next example, the numbers given are the first 4 partial sums. We're going to form the series and then from that determine the convergence. So you can probably already kind of guess looking at the series. So this is not the series, this is the sums. So we're adding more and more terms, and these are our results. So what you can see is it's getting bigger, but it's not getting bigger very quickly. So we're going to look at the series itself by finding the terms. So what I'm going to do is create a chart. There's different ways you can do this. This is just a way to organize it. So we've got n equals 1, 2, 3, 4. The partial sums are 8, 10, 10 and a half, 10, and 5/8. So if the sum of the first one term is 8, then the first term is 8. If the sum of the first 2 terms is 10 and the first term is 8, that means the second term is 2. If the sum of the first three terms is 10.5, that makes the third term equal to 1/2 and 1/8. So our series is 8 plus 2 plus 1/2 plus 1/8. Well, we already kind of said that it's increasing, just not a whole lot. But now if we look at this series written out, this is an infinite geometric series with a common ratio of 1/4. If we have a geometric series whose common ratio is between -1 and 1, then our series is convergent. Next series with partial sums is going to be 2, 6, 12, and 20. And again, I'm going to make a chart. So in my chart, my n is 1, 2, 3, 4. And we've got 2, 6, 12, and 20. So if the sum of the first one terms is 2, my first term has to be 2. If I'm adding 2 terms up to get 6, that means my next one is 4. If I'm adding 3 terms to get 12, and the first 2 are 2 and 4, that gives me 6. This one's going to be 8. So you can always just subtract 1 minus the previous one. That's maybe an easier way to do it. So this series is 2 plus 4 plus 6 plus 8, and so on. Now again, from the beginning, we could have seen, well, these are getting bigger, and they're getting bigger quicker. Which means it's probably not going to be a convergent series. But now when we look at the terms themselves, the terms are getting bigger. In fact, it's getting bigger by a common difference of 2, which makes this one arithmetic, which means it is divergent. All right, my last example here. What does the following information tell you about the series? Now this is a little tricky because it looks very similar, but we have two different series. One where an is 3n minus 1 over 4n plus 2. One where Sn is 3n minus 1 over 4n plus 2. So the difference obviously is what is equal to this formula. An are the specific terms, which means if I wanted to generate this sequence, I would be plugging numbers in here. Well, if I look at the limit as n goes to infinity of that, well, let me start. We're taking the limit of an. 4n plus 2. So this limit is going to be 3/4. Okay, the degree is the same on the top and the bottom. But what we are taking the limit of is very, very important. So here we're taking the limit of an, the specific terms, which means as n goes to infinity, the terms are going towards 3/4, which means we're adding 3/4 plus 3/4 plus 3/4 plus 3/4 infinitely. This is the divergence test that we talked about last time. If the limit does not equal 0, if the terms themselves are not getting smaller and smaller and smaller, then this series is divergent. Versus if I look at the limit as n goes to infinity of Sn. That limit, the limit itself is exactly the same. The limit is still 3/4. However, because what we are taking the limit of is different, we're looking at what's happening to these sums. So this is saying these sums of however many terms I want is gonna be 3/4. 1,000,000 terms, sum is 3/4. 2,000,000 terms, the sum is 3/4. So the sums have a limit, which means this one is convergent. We use limits in a lot of these different tests. And those of you who are going to look at the ratio and the comparison test, we again are going to be using limits. So what specifically you are taking the limit of will determine what's happening. If the terms themselves are going to anything other than 0, it's divergent. But if the series has a limit, it's going to be convergent. So that is the difference between the divergence test and partial sums. and how you can have the same value and get a different conclusion. Thank you.